Hello everyone, in this video I'd like to share my effort that I considered to train my very own Katago network from scratch, assuming a very miserable and old hardware and CPU only training. And generally I want to answer this question, uh, not how long would it take to create a reasonable net using my setup, but rather what would be the estimated speed of improvement of the neural net. So obviously, with my setup to achieve like modern Katago network strength, it takes probably, I don't know, 10 years or something because I have a very miserable hardware. But with a very initial uh, six residual block network and 96 convolutional layers, which results only in 3 megabytes network. That's the network from the very early Katago releases, one of the first networks ever. That one is possible to train, even assuming my miserable setup. And also, what I was wondering is that if I can set up everything and if I can understand how to invoke this pipeline, create the development environment, etc., etc. So that was the thing. And interestingly, the results that I got so far are quite impressive, not in terms of the overall resultness or something, but impressive because I can see with my eyes, I can see the difference how every next network instance that has been trained, how it's better compared to the previous one. And if I run it, if I run a self play within the GoGUI, for instance, to see how it behaves, like the different versions, it gets really, really interesting. So I'll probably demonstrate a few networks that I've trained for the last, it's almost a week now, maybe 4 days, 5 days. I'm not sure how long did it take. It's very miserable training row wise and training sample wise. And again, before we get started, so essentially, when I started this, I didn't realize that if I only want to see what would be the actual difference between the different states of the train networks, I didn't particularly even need to run this on my own. I could go to the Katago training org and within the releases page, so here, I'm sorry, where is the 85, 805 networks? Yeah, so down below in the very bottom, so not the current most stable network, but down below the very bottom, um, starting with this one. So Kata random is not interested because this is the random network. This one is also quite random, pretty much. So if you just try to download, like say this one, and then say this one, and then say this one, then you would see that this one is like almost random. Somewhere over in here, this is like 20Q maybe. And the strongest one is around, the strongest one is around OGS 4Q. That's a very rough estimate. OGS 4Q, in case if no Monte Carlo research is used, I mean the bare network with a one single playout. That's the very difference because you may blunder. Like the later networks that like more than 100 megabytes in size, and instead of just having 6 blocks and 96 convolutional layers, the latest networks to have 28 blocks and 512 convolutional layers. It's not probably even, I'm not sure what the NBT stands for. Yeah, 512 convolutional layers. So this is like immensely bigger. So like 20 megabytes or something for this one, I'm not quite sure. So these are quite huge. And obviously these networks are immensely stronger than the original ones. But interestingly, that for the old hardware, using this, even the smallest 6 block network with the 96 convolutional layers, the latest version, like for this one, say, it might be a solid level, assuming the Monte Carlo research might be quite good. So you can beat this network if you're a pro player. You may beat this network. So yeah, again, so I could just download the various states. So these, like this network, next one, next one, next one, these are the iterations. And the difference is that the amount of, so this is the number of training rows. The training rows, as ChatGPT explained me, training rows are the unique positions that has been generated from the games of a self-play. So it goes for a self-play loop. It generates SGF files. Those SGF files are later converted to NPZ files, which are the binary representations of those games. Not exactly the binary representation of games, but binary representation of the unique positions that should have been used as a training data. They are being shuffled in various interesting ways, which we'll probably talk about as well. And again, like so here initially was like 500, say 500,000, uh, and that is like twice as much. It's already like 1 million. This already to go in these big chunks, it takes much more random access memory than I have. I only have 4 MB and machine them running this, and also like yeah, mostly random access memory. GPU wise, I mean, if you don't have a GPU, it just would be very long. But the problem is not it's going to be very long. The problem, probably like training process gets terminated because you're running out of memory. So that's one of the biggest problems that I've encountered with my low level resources system. So for me, I'll now show you my numbers. So for me, it's like every next one is like 100,000, 200,000, 300,000, something like that. And from this particular rows, there are a number of training samples that has been generated, which has duplications, but that somehow serves the training purposes. We're not quite sure exactly that works. So this essentially means that the progress that you can observe here is much bigger and much faster as opposed to the progress that I may observe with a much smaller chunks. And this is also interesting because for this, if you download and try each every model to try, like say you download the model, then you connect the model to the Katago, and then you run the self-play in the GUI, like the Go GUI, play against its net plays against itself, even with a single playout. You would see, I don't want to say dramatic change in playing strength, but it's very like it may not be that clear like it was like blundering everything, and next iteration it already starts killing groups, and you don't particularly see how that happened. So the chunks are a little bit too big to see the all these intermediate differences, like how exactly it has been evolving. So the evolution is not seen that nicely. It's seen generally like you understand that it definitely gets stronger every next iteration. But so again, because of the low resources that I have, what happened to my experiment was that I can observe the growing of the net in a much smaller chunks, which is more interesting from the human perspective to see how exactly Katago learns. And this brings very interesting insights as well that, in some respect, explains the playing style that it comes up with eventually. Also, so just to give you a clue, like how Katago training is generally different. So before I go to showing my training process on the remote machine now, I'll now show you that. I just want to say I just want to tell you what's the major difference between the learning process between Katago and humans. So for humans, as human players, we start with getting to know the basic concepts like stop playing in the corner. Like probably the very first lesson you would get from someone who knows how to play Go, he would tell you the first 4 moves, Like the first moves generally should have been played in the corners. Then it tells you that you first need to play in the corner, then approach an opponent's corner, then take in the side. So human players know that corners are the biggest, then sides, and approaching opponent's corners are also good. So first try to take big points, and then the rest. And then eventually this comes to fighting and killing groups. So fighting and killing groups is like the very last and the most probably difficult thing to master on a high level. For the Katago, it's a little bit the opposite. So Katago, so I just want to say that, say somewhere in between. So say this one, block 6, condition list 96. So the eventual version of this net, the smallest net, assuming one play out and no more. This is like OGS full Q. It's like Fox 1 done. Essentially, this is like Fox 1 done. I tried this net to play against Fox players. It's like 50% winning rate, so it's like literally it's Fox 1 done. And this version already knows that you have to play in the corners first. It mostly goes for territory. It mostly plays Kamoko points, this version, if there is only one play out. If there are more play outs, I may play differently, I don't know. But with one play out, it mostly takes Kamoko points. And somewhere in between, say over in here, it doesn't still know that you need to play in the corners. And it may start with the moves that look super weird from the human perspective. Yet, the playing strength over in here would be like around 10Q. So for a 10Q who knows that you need to first to take the corners and then everything else, if it would be playing somewhere around 10Q or somewhere around OGS 10Q Katago Nat over in here, say, that you would be very surprised with the fact that it knows nothing about the need to take corners and the sides first. Essentially, it starts fighting from the very beginning. Even human players who prefer fighting, and they just play first few moves in the corner, and then they just start random fighting. It's very similar, apart from the fact that this net is not going to play the first few moves in the corner. It just starts fighting, and sometimes it's really like around 10Q strength. I don't know, this one, maybe somewhere in the middle, let's say. It does play at that level without having knowledge that a human player of that level usually has. So it might be thought of from bottom to top approach. So if human approach like from top to bottom, so you know what is good, what is bad first, and then going down, you learn how to apply those skills. For Katago, it's the opposite. It starts with fighting skills, and based on fighting skills, it then learns that the strategies are to take the corners first, etc., etc. And he learns about before 10Q, say Katago 10Q, which Katago Nat, which is around even to human OGS 10Q, it doesn't even try to play for influence at all. 10Q OGS players might try to play for influence sometimes. They already good enough, understand what influence is, maybe not at a very good level, but they do understand it. But Katago knows nothing about this, but it fights already good enough to beat a human 10Q player. So, why am I telling you about this? So, it was very insightful for me to know that the order of skills that Katago is mastering during this self-plays is vastly different from how we as humans improve and go. This is very interesting. And especially because I have much smaller chunks than this, I can observe it in even greater details. So especially like semi-random net beats almost random net. From the human perspective, it makes no sense. But from the Katago perspective, it makes perfect sense because this net is clearly stronger than this one. This net is clearly stronger than this one. And even if we go not like 500,000 times more training rows every next iteration, but even if we just consider 100,000, like I do, that is also enough already to see the difference. And it might make no sense from the human perspective at the early training stages. However, this gives you an idea how Katago reaches its superhuman capabilities. Because one of the biggest reasons, in my personal opinion, why we as humans cannot go beyond this superhuman level that Katago achieves is because we are really sticking to what we know. And Katago never sticks to what it knows. So every next iteration, it literally says, okay, what I knew so far is crap, and I need to go further. I need to reveal something new. And we as humans, you as a human, you would never say playing in the corner is bad. You would never ever question that. And although playing in the corners is generally obviously good, and no one says you need to play somewhere else in the opening, but the general idea from the human perspective, this is incredibly complicated to get rid of the habits that you have gained throughout like years of playing Go. You like used to do things the way you used to, and on the one hand, this gives you your playing strength, your current. Say you're like 5 dan, all the habits you have as a 5 dan are super cool to be the 5 dan. Yeah, but if you want to become 6 dan, 7 dan, 8 dan, 9 dan, you might have your 5 dan habits to be as bad as 5q habits preventing the 5q to reach the 1 dan. This is exactly the same thing. So Katago is really free from the envisioning that it has. It's really free from like its understanding. It just goes further and further. And when we observe this in small chunks, it's interesting because this very small changes they accumulate, and eventually they result in a very very strong game. So like when I've been playing around 10q Katago now from somewhere in between in here this list, it felt like as if I'm playing someone who probably feels stronger than 10q, maybe as if I'm playing the guy who fights at the level of, say 6q, maybe. In the meantime, he never heard of the fact that he needs to take the corners. So this is how it feels like you're playing the 6q who knows nothing about taking the corners. And you still can beat him, yeah, surely. So this is a very interesting, yeah. Um, Okay, let's go for a demonstration. Demonstration. Yeah, obviously you can download this games if you want to know how the very early Katago is playing. You can just download here and see. But what you cannot download, at least for now, maybe I would publish this one day, maybe not. I don't know whether it makes sense or not at the moment. It's really hard to say. But I want to show you my experimentation, and maybe before that, a very quick overview of what do you need to how can you train Katago on your own. So after you compile the after you compile the repository, and after you do compile Katago on your own, and that's needed, say, because, well, one of the reasons the libzip library that exports the nets exports the training data into the NPZ format. I think that's related somehow. Also, the eventual nets. So this compression related stuff, not quite sure exactly where that takes place, but compression takes place in compressing training data, in compressing neural nets. Also, yeah, GZ format, being GZ format. So you need the leap GZ or leapz. I don't remember. So if you use the Katago version from the release, it might not have that, or might be limited, or whatever. So they do recommend compiling Katago on your own. That's what they recommend. So assuming you have the Katago compiled, which is not very hard to do, it's over in here, compiling Katago. It's like I'm on Linux. I'm not sure how it works on Windows. So it's quite simple. You just I was using exactly the again backend because the CPU only is what I'm looking for. I don't have the GPU, and I wasn't using AVX2 because I don't have that. I have a very old CPU, so I don't have the AVX2. Yeah. Although, hey, this is interesting. It's a bit different computer that I'm using now. Maybe it already does have the AVX2. I don't even know. Yeah, it just made me wondering suddenly. Uh, Maybe I should recompile my Katago. It would probably dramatically affect the self-play speed. Yeah, making videos makes you wondering about the steps you've considered before. Okay, anyway, so yeah, definitely to make to maintain the to-do list during recording the video. Okay, so compiling Katago is quite simple, and then uh, there is an entire README for how to train. It's generally mostly it's quite easy. Self-play training. So what I've been using is the synchronous training on a single machine. It also supports asynchronous training many machines at the same time, something like that, for like distributed training. And you also can contribute self-play games, but that's a totally different story. So I was interested in single machine synchronous training, and the main loop to start that is this one. Under the Python directory self-play synchronous loop shell, and we go exactly there now. So Python and self-play. So here it would create after I run the synchronous loop. After I run the synchronous loop, it would create a new folder with name, the name prefix for the net architecture as well. So there are a few parameters to specify. They all are listed. If you just run the synchronous loop, it will tell you that you need these parameters: name prefix, base directory, training name, model kind, like 6 block, 96 convolution of layers, and use gating. Gating means playing against the new model once it has been exported to make sure that the next model is better than the previous one. A couple more files to have a look at, which may speed up things. Self-play CFG and gatekeeper CFG. So mostly for the parameters of how many playouts the self-play is using, and the gatekeeper how many playouts are they using. So I set the self-play to 10 or something, gatekeeper to 20 maybe. I don't remember. So these are the files that I had a look at, and has been changing the number of max playouts to make it not lasting forever, but some reasonable time. And the main training parameters are here. So these are the basic ones. If you have a computer better than mine, which is most likely the case, this should work for you out of the box without changing. So I started with only 10 games and minimized the rest of the values. That was not working very nice. Then I tried 100 games. That also didn't work very nice. Then eventually I started using the 500 games, but I used 50,000 instead of 100,000 train samples per epoch. One epoch results in creating a single neural net as an output. So 2 epochs, there would be 2 nets. It sounds a bit strange because usually epochs do mean that for a single net you probably make it several epochs. Maybe because it's the policy of saving checkpoints and exporting in this exact way. It's a little bit hard to say. Anyway, the rest of values also, I just minimize them around half, something like that. Because before that, I was running out of random access memory on my target machine, and this didn't quite work. But after I experimented, I came up with the values that actually work. I managed to run a few cycles successfully, and that was good. So essentially, it runs with an infinite loop, and the process of training is the following. So if it starts with a gatekeeper. Gatekeeper is the Katago mode that allows you to play the new net versus the old net, with an idea to tell you whether the new net is better than the old one or not. So the gatekeeper is looking at the current working directory where your net has been created, and it asks, it sees, just looks whether the new net exists or not. If it exists, it tries to play against the previous one. If it doesn't exist, it just skips. Then the self play. So if the gatekeeper considered the new net to be better than the previous one, then the self play starts using the new net for a self play. If not, it uses the old net. If there are no nets at all, then the self plays creates the random net and starts the self play with a random net. Shuffle creates the actual training data from the games generated by the self-play. And here the idea is interesting because like all these parameters. So interesting parameters is shuffle keep rows and this taper window. The idea is that say you trained 100,000 you have 100,000 training samples that has been generated by the random network. And then another 100,000 examples has been generated by the next iteration of the network. So it's still quite pretty random, but not as random as the actual random one. So when it comes to using training data for the third iteration of the network, it would most likely be using the data provided by the second one and a few from the first one. So try to wrap one's mind around this, how this works. Every single training cycle, the training data that is used is mostly the training data that has been generated by the previously accepted neural net, plus some percentage of the training rows from the previous one. So this is done. I'm not sure why exactly this is done that way, but they explicitly say that the rows that should be kept needs to be larger than the maximum number of training samples per cycle. So this ensures that you also do use the training rows from the previous net generated self plays. I'm not sure why exactly that is needed, but that's what they suggest. It's not obvious. You probably may ignore it, but I'm not sure how the training process would behave in that case. So this is something, and the taper window, if I'm not mistaken, it defines the like how many. I guess this means that the 50,000ths of the training rows would be taken from the previous iteration of the self play. But I might be wrong. I'm not 100% sure about that. Not sure. So, also quite important thing, you need to have PyTorch being installed. I was using the virtual environment, which worked well, and I was afraid that sometimes it's very like when it was TensorFlow back in the day for Katago was very difficult because TensorFlow 1, TensorFlow 2, all this version how you never know which exact version you need to use in order to make it compile and run, like not compile and run, just to make it run, because the code might be relying on some no longer maintained functions, etc. The way how the waiter initializes is just a fucking hell, really. But after they switched to PyTorch, this is much more easy now, much easier now, because now you just do pip install PyTorch, pip install Torch, and that's it. And it just works. You don't need to care about anything. So finally, for those who didn't yet go away and still watching this video, I will now demonstrate how the actual training process. Oh, don't need the browser. How the training process is working. So I would now invoke the remote desktop. Just make it full screen. So here is where it runs. Currently this is the stage of self plays. It played 230 full games. It lasts for 3 hours maybe already, and it needs a couple more hours apparently to generate. Yeah, maybe not a couple more, but yeah, 3 hours more, or even a bit more, to generate another 250 games to make it 500 games overall. So the current neural net that generates games via the self-play is this one. So it has 280,000 samples, has more, training rows, 280 training rows, and these are the samples that are generated based on from these rows. So here there might be duplications, as ChatGPT explained to me, and here these are the unique positions. And you might know these values from the names of Katago networks that you might find online and download them from there. So before this, before the self-play, the previous, the loop starts with, not with the self-play, actually, the loop starts with trying to play the match with the gatekeeper. This is the last time I started the loop. So the gatekeeper is looking for a modal, the last accepted modal from the modals to be tested, and it finds the modal that is called this one. So essentially what's happening. So after I run the synchronous loop, I'm running this within the virtual environment, so that PyTorch is also available, at least within the Katago environment that is created by the command of Python 3 -m virtual environment. And the Katago environment is the folder name, and then source, bin, and activate to make PyTorch available within this session. Is this really represented here? It should have been, but I'm not sure if it. Okay, it doesn't matter. It's probably not displayed the way. I don't remember. I don't quite remember. Okay, it doesn't matter really. So the gatekeeper it starts looking for. So CNK train. This is the working folder. It looks into the modals to be tested. Now there is empty. It's empty because it tested the modal, and successfully the modal that wins gets to the modals. So this is the current best modal that runs the self-play. In case if modal is losing to the previous modal, it gets to the rejected modals, which also might be the case. But this one got here not because it lost the match, but because this is from the previous epoch, and it just happens that I have more samples than needed for a single epoch, so it just rejects the previous version without even testing it. That's what I experimentally came up with. So if I didn't play 500 games, maybe if I played 250 games, then I could be updating in smaller chunks. But it also might happen that it could have been rejected anyway. So it's not very much of a difference playing 250 games and then run one epoch, or play 500 games and run 2 epochs and use the net from the second epoch, and then automatically reject the one from the first epoch, if that makes any sense to you. Okay, so eventually modal that the new modal that beats the previous modals appears here. So this modal did manage to beat this one, this modal did manage to beat this one, and this modal did manage to beat the random modal, which is not saved here. Alright, so currently we are over in here. Am I running the... no, I'm not running the... Let me run the... Not like this. Let me run HTTP server so that I could share the files. Because the CPU load is like very crucial, very big. So if I do the system monitor, I don't want to run anything on this computer because it's like CPU 1, CPU 2, 100% load. Lots of memory has been consumed already. So if I run something on this machine, on this remote machine, I may just crash the training process. I don't want that to happen. I only want to take the modules. So I start the HTTP server, and then I can go away from here and just close it. And then I may open the web browser. Make sure that the downloads are clear. Okay. Okay, why didn't the web browser start? All right. So if I go to, so these are the neural nets from the remote machine. So starting with the very first one, just want to give you an idea of what would be the difference. So modal bin gz, keep, and downloads, cut. This is a separate Katago that I have on this machine, so paste, overwrite. And within the Go GUI, I already have the configuration to run with this exact network. Attach, Katago CMK module. To make sure that I'm not using some other module, I may look at this here. So module is used, Katago module, and module name CMK net, and then these values. So samples 109376, data rows 112529. And here, it's not here, but it's over in here. The one that I've been using is this one, 109376D112529. So I just checked that the module that has been loaded into the Go GUI is exactly this one and not anything else. So if I ask now make computer color both, it's only one play out. It starts playing the game. It's almost a random play, almost playing random moves. I'm not going to be showing you one net is winning against the other because even those wins do exist, they're not very obvious. But even the very first modal, you see, like, eventually white did manage to make some territory, and black did also manage to make some territory, and also white here. It doesn't know about two eyes at the moment, not very good. Also, this is that. So black has crushingly won the game, but just to give you an idea how this looks. So not very impressive, but this is exactly how he thinks of the game. I can also play against the net, but doesn't quite make sense because it essentially doesn't answer my moves. But visually, I would now show you the next version. Well, maybe a couple more games just to give you a visual clue on how this works. This starts like in the random position of the board. It doesn't start with the center or something, or with a corner or something. But another way to inspect the actual difference in weight might be using the laser GUI, which I will now show you. Essentially showing in both probably makes sense. It looks like the game of Go already, so this net already beats the random net, which is interesting. It looks like the game of Go, and it's even the very miserable amount of training rows, only 112,599. It's very miserable, but it already tries to build some territories. Yeah, it's very interesting. So, if I now open the Lisa GUI, and let me just figure out which one. Yeah, this modal bin GZ. This one. Yeah, my poor Raspberry Pi would now fly above the table, really. Okay. So you see, like, the analysis in the very initial position looks not like it looks in the normal Katago. You see? So you just visually remember the pattern. So yeah, it's like goes like this. So after a few playouts, it gets changed, etc., etc. So yeah, it looks a bit weird. You would never see this like weights like the normal Katago engine. Just to give you an idea, it's vastly different, really, with the same exact position, just visually different because the weights are totally different for this one. Um, okay, I probably want to reload things. I don't know. Yeah, so this is a normal category. See, it's vastly different from what we've just seen. However, the pattern, you just visually remember the pattern for this one, and the next model will already be different because the weight would be changed after the training. So just remember this visually. Okay, then we go for the next one. Say this one again, model being GZ, keep, and cut, overwrite. And now again, so detaching here, attaching you, so make sure, so this is already a different one, so 379.296 to 374.25. So this is it. So this is another model. So it's less, three times, no, not three times, maybe twice as much of training rows and three times as much of training samples. Maybe not three times. So it's more data, and the first net was trained on the games produced by the random net. And the one that we would now see how it plays against itself has been trained on the games produced by this very net that we've just seen. Like, so the next net that I would now load has been trained on the games produced, the games like this. So this are like much better than the random games already. So go into new game. Oh, it's already there. Okay, computer player, both. You see, like, it plays differently. It might not be obviously better from the human perspective, but you see, like, it just behaves differently. It definitely has like different playing style. You see, it's just different. Interesting, yeah? It's just different. So it learns something new and tries to play in a bit different way. It doesn't necessarily mean this is stronger, like, from the human perspective. But again, this net that currently plays did manage to win against the previous one. And that's what the gatekeeper is needed during the training process. Let's have a look at one more game. It definitely has a different style, it's visually seen. And it would also be reflected within the. It just saved the group. Did you see it? It just managed to save the group. Not for a long time. It still dies. But yeah, this is cool. This is really cool. Maybe you get more motivation watching this silly games by Katago when you try to play the real Katago, good, nicely trained Katago network next time. You would know that it was as bad as you, maybe even worse than you were ever. This is motivating, yeah. So this is another game, you see. So now let's just detach this one to not overwhelm the operating system with too many Katago processes running at the same time. And again, going back to Lizzie, just to show you that the pattern is going to be different now. It's already working with a new modal bin GZ because I've updated, and it points to exactly the same location. As you can see, this is different from what was in the previous part. The weights are more smooth, maybe. It doesn't have that many preferences that it did in the very first, in the initial run. So it's like everything is even. This is what it says. It tries to play the first move on the board edge, which is super weird. But again, these are still the very early phases of training. Okay, so it's like a completely different pattern when you see the analysis. It's totally different. Right, and finally, I want to run the last available one. So this model that I would download now, it took around 4, maybe 5 days. It was quite long. I was making mistakes, so it took a bit longer than it could take. But again, like essentially purely, it's around 4 days or something to get the result like this. I hope I did download it. Did I? Cut. Yeah, suggest overwriting. Oh, hold on a sec. Nope. Okay, let me just clean up things. Let me clean up things. Okay, yes, keep. So, go in here. Okay, so let's 528 280. Okay. Five two eight 280, right? So this one. Yeah, by the way, the previous one, not much more samples, to be very honest. Not much more training rows, although much more samples. Yes, interesting, really interesting. So, game, new game, don't save, and just computer color both. It's even more different, you see? It's even more different. It's about building walls all the way along. It's about trying to make big groups connected, trying to live. Yeah, still going to die. Cool, isn't it? Yeah, and it managed to kill. So this is how Katago learns to kill. Yeah, this is that, unfortunately. So this already looks like the game of Go, you know? Already looks like the game of Go. Okay. Now say you want to evaluate this. So how good this network is, and there is also the way to do it. So if I just save this to my Go rank estimator game SGF, save, replace, and go into Go rank estimator, and use the existing one. So now it evaluates the game that has been just played using a normal 10 block 128 convolutional layers network. So I would now have an average estimation of the rank of this Katago network for both for black and white. Unfortunately, I didn't show the rank estimation for the previous versions because within this level, although every next network is better than the previous, but objectively, it's not necessarily better evaluated in terms of like absolute playing strength. But sometimes after a few cycles of training, I think running this might make sense. Oh, and the results are quite interesting. So it's like 59Q for black and 66Q for white. Well, usually for this network, I got 90Q and 100Q. So this results are quite satisfying, I need to say. Just to give an idea that this is still very random. So if I just play another game, it might be evaluated much worse. Just to give an idea, or much better. It's still not very clear. So you say like it tries to have a grip over the entire idea of I don't know what exactly. Yeah, this wasn't very clever. This wasn't clever. But this is how Katago learns. It's not very clever, but this is how it learns essentially. Super interesting, yeah? Yeah. It could die with its own group, but it killed. It didn't die. This is good. Yeah. So it's already something, really. This is something. It looks super weird still, but this is something. Yeah, let's try to save this one. Save. Place. And try to run the estimator again. So it was like 69Q or something the previous time. Let's see how much. What would be the Q this time? Yeah, probably, I don't know, probably next time, the next video will be when I don't have enough patience to wait to continue training. So maybe after a month or so. My goal for now is to train the Katago NAT to the state where it can beat me. So I'm 9Q on OGS and 8-7Q on IGS. So it won't be very difficult to beat me. Yeah, now you see, like now it's much worse. It's like 83, 83rd Q, 77th Q. It was like 69th Q. So the previous game was, it goes into a normal AI, it goes into a normal Katago NAT. If it thinks like that was better, the previous game. But again, at this level, it's too early to judge. But I just wanted to give you an idea that we can somehow give an estimate rank. So this is like from the human perspective, maybe from the human perspective. So how likely it plays. But again, the around 10Q version that I've been mentioning early in the video, it was like not playing the corners in the very beginning, yet playing the game of around 10Q level, which was also quite cool. So yeah, guys, I think that's it from my side. Thanks for watching. And yeah, probably next video on progress of this Katago network training with a bare CPU with very low resource stuff is going to be in the next video. Yeah, I was mentioning the low resource. Let me try to tell you the exact low resource machine that I'm using. The exact one. Yeah, Intel Celeron G1850, 2.9 gigahertz, 2 cores. Yeah, quite an old one. And yeah, oh, it's even had the graphic cards. Interesting. Mm, it's not using CUDA for Torch. It's using CPU. Mm, I don't know, like either no drivers for this one. This is a placeholder video card, or maybe okay, or even this is the embedded one. Yeah, probably this is the one that is embedded into the CPU itself. Yeah, yeah, core processor integrate. Yeah, this is not a real graphic card. This is the CPU integrated one. So yeah, there's like CPU usage anyway. Yeah, I'm very dumb in hardware, so cannot say much. But just to give you an idea, what is the machine that I'm running this Katago training on? So it's quite an old machine, quite a miserable one for the purposes of training neural nets like the Katago is using. Yeah, guys, this is it from my side. Thanks for watching. Hope to see you next video. Until then, and cheers.